and we using this both for physics and science. So there'll be first part here deals with lenses. A lens is a glass, and we're going to have two types. Typical lens. When you have a lens, you know, an IP, you know, type of lenses and glasses. I have glasses, and lenses go back many centuries. Glasses go back many centuries. And the idea of a lens, what we're going to have, and the example is from the lab, a handout, and then what you have is if we have light from an object or light source, passes through the lens, and then will form, if we set it up right, a real image on a screen. And we'll be talking about this in the lab today as far as that's concerned. So this is part of lenses, and we have a lens. So a lens has what we call a focal length, F. F. And that means that if we have light from a long way away, say, I mean, it could be just a few meters, it will focus to a certain point here, and this distance is what we call from the lens to where the light focuses is the focal length. All right? So that we do there. So a lens has a particular focal length. Now we're going to be using for this lab different kind of lenses. And lenses we will be using, they will have an F of 10 centimeters, meaning the light from far away will focus on a screen 10 centimeters away. And we'll be using one that has 20 centimeters. And these are both what we call convex lenses. All right, they both have focal length positive. Now, on the other hand, if we have light, a lens where instead of the edges being thin and the middle being thicker, we have where the ends are thick and the lines and the middle is thinner. This is what we call a concave lens. And in this particular case, this has a focal length, meaning if we have light, I'll show this the handout. If we have light coming from far away, it actually spreads out, so the focal length would actually be in front of the lens. So the light would actually spread out, and so the focal length is in front, and this will be a focal length less than 0. And in this case, we're going to have is F is minus 15 centimeters. So let me compare how each one works, because I'm kind of jumping here. We take a convex lens, and I'll show you how this, and look through a convex lens, you notice how everything is upside down, right? We got the things on the table in the back, and they're all upside down. That's what a real image is. It's going to be what we call inverted, right? So the image will actually be, image is real, meaning I can actually form it on a screen and it'll be inverted. All right? So a real image is the image we can form on a screen. I'll go through this whole lens formula then. So that's a convex lens. Concave lens, on the other hand, like this one, if you look at that, as opposed to being A concave lens, when you look through it, the image is still right side up, right? We cannot form a real image with a concave lens. So the image is what we call virtual, meaning you can't show it on the screen. You can see it through your eye and it'll be upright. So that's the first things here. So we have focal length, which we define for a convex lens or concave lens. A convex lens has an image that's real and upside down, inverted. A concave lens forms what we call virtual image. It's not real, it can't show on a screen, but it's upright. You see with your eye, because your eye is another lens. All right? Okay, so that's the first part there. All right, moving on here. So I'll leave that. And for this lab, you'll be using the handout. So what we have here is if we have a lens which has some focal length of, and I'll use the ones we're going to use for the table. F is 10 centimeters. And the way this works, we put an image, an object, say a light or me or whatever, a light source, a distance P away. This is the object distance. All right. It will form an image inverted. And we call this Q the image distance. And object is the distance from the source to the lens, the image distance from the lens to the screen. And the lens formula is given by 1 over F is 1 over P plus 1 over Q. All right? So what we're going to do here then is for the lab is to have given a focal length and an image object distance, we're going to calculate where the image should be. So we're going to want to find Q given P and F. So the way we do this is we rearrange this. 1 over F is 1 over P plus 1 over Q, and you can go through the algebra yourself, and what turns out to be is that Q is then given by P times F over P minus F. All right? So let's do one example, and then you'll do the rest of them yourself. So I'll go through the rest of them. As far as I'll do that, you're going to calculate all of these. I will do the experiment, and then you can get the percent error. So the first one will be P is 15 centimeters, F is 10 centimeters, I believe, yep. So then Q would be 15 times 10 over 15 minus 10, which would be 150 over 5, would be 30 centimeters. So that means that with this particular focal length, with P being 15 centimeters, the image distance should be 30 centimeters away. So that's what we would have for that one. All right? So now we'll do the experiment. Now, another thing here is this is our lens formula, and this is how we calculate Q. But what's also true is we have an object height H0 0. So this has a certain height. The image will have a certain height. And it turns out that the ratio of, and this will be negative because if we just take the values, this will be inverted. The ratio of Q over P will be equal to the image height over the object height, is what we call the magnification M. So this is the magnification. And what we would have for this case is we would have Q is 30, P is 15, so the image height, the magnification should be 2. Okay. All right, so for the lab, as well, go through it, the object height is going to be 2 centimeters in each case. I'm going to have P for different, so all I'm going to do is have the first lens, do 3 different measurements, calculate, you can calculate what Q should be. I'll let you do that yourself. I did this one, and then we'll do is go through the experiment and get the percent error. The bottom part here, I just did, like what happens if you look at a distant object through a concave lens, it's going to be upright. All right, so let's go do the lab now. I've got it set up. All right, here's our light source with the 4. Here's our lens. And here's our screen. And I'll show you what happens when we adjust the image distance so that it's what it should be. And as it comes into focus, all right. So what we're getting is a real image that's upside down compared to the original object. And in this case, if the magnification is 2, it's going to be twice as large. So this is one example here of where the object distance was 15, the image's distance was 30, so the image is magnified twice and it's inverted. Okay. All right, so in the first case, we have object distance is 15. This is at the 100. This is at the 85. So this is 15 centimeters. Then I've adjusted the focus. So here's the light source. Here's the lens. Here's the image. It's at the 55. And so this is 30 centimeters. So that here to here is 30 centimeters in length. Okay. The next part will be, I have the, again, focal length is 10. We're going to move it to 20. We'll make the object distance 20. So I'll put it at the 80 centimeter mark. And then what I'm going to do is you calculate where Q should be. And I'm now going to experiment where it actually is. and it's at the 60 cent. So this is 20 and this is 20. So P is 20, Q is 20. So then you can figure out the magnification based on the fact of P and Q being equal. Next, so that's that part. And I'm going to do is then for F is 10 and P is 30. So I'll move this back. All right, then move this 10 more centimeters. And in that case, I'm now going to adjust. So P is 30. And in this case, so P is 30, Q is at the 55. 55 minus 70 is 15. So that's P and that's Q. And then you can look at the magnification and then see is the image, should the image be larger or smaller compared to the object distance? Right? And we can actually, we'll look at that. All right, so for this case, we have object distance is 30. There's our object height. Image distance is 15 based on measure. And then you can see what the image height is based on the ratio of PQ over P. All right. All right, this is for the next part with the second lens. In this case, we have the thinner lens, which has a focal length of 20. Okay. You can then calculate. We're now going to have the object distance be 30. So this is at the 100. This is at the 70. And then we'll figure out where the image should be. All right, there's where it's focused. So when the F is 20, the object distance is 30. It focuses where the screen is at 10, and 10 minus 70, so that gives us an image distance of 60. All right. So that's the first one. The second one we're going to do. All right, when the object distance is 50, all right, we calculate the image distance, and based on focusing that, it focuses right at the 17 centimeter mark. So 50 minus 17, this should be 33 centimeters. Okay. The next thing we're going to do is for the last case is for P is 60. F is still 20. So we'll move this out 10 more centimeters. and then focus, bring this in to where and it turns out to be right at the 10 centimeter mark. So if this is 60, we measure, and this is at the 40 mark, this is the 10. So for the last case of P is 60, we get Q experimental is at 30 centimeters. So from there, again, the magnification is given by the image height divided by the object height that we just talked about before. So that is the lab as far as that's concerned, and you can do your data from there.